Hi, Dr. Charles Martin here with Calculation Consulting. Today, for the next hour or so, we're going to be taking a look at a really exciting advancement that's come out of deep learning in Google Brain this year called capsule networks. Capsule networks. Developed by Geoffrey Hinton at Google Brain and his collaborators, this is a very, very exciting development in visual processing. Something that Hinton actually has been working on probably since the 80s. And it's a pretty exciting time to see him to be able to produce actually 2 papers on the subject just this year. The first, Dynamic Routing Between Capsules, which is published with Hinton, Sara, Sabour, and Nicholas Frosst, is a pretty interesting paper. And we're going to dig deep into this, looking at the science that motivated it, some of the mathematics that they're using, and an existing implementation in keras, so you can go and start working with it. We're also intermittently going to take a look at a second paper, which is now under review as a conference paper in ICLR 2018 called Matrix Capsules. This is a generalization of dynamic routing using matrices and some fairly sophisticated mathematics, actually some chemical physics. So it's a pretty exciting talk. It's going to take some time, though. We're going to look at the science that motivated Hinton and why he has been pursuing this for so long. And we're going to take a look at how the science and engineering play off and looking at some of the advances in convolutional networks and max pooling and how this stuff is actually implemented today. So let's get started. This is a really can't emphasize enough how much interest there's been in this. Here's an article in Wired magazine. Google's AI wizard unveils a new twist on neural networks. Yeah, that's a pretty good article. There are a number of videos and presentations on the subject. And what I'm going to hope to do today is really walk you through the complete area from my understanding of it, starting as a graduate student and really a postdoctoral fellow in theoretical physics and neuroscience and what we understood about the brain in the 1990s and where we've come to today. So if we start with what is our most common application that we have with neural networks, it's convolutional nets, things like optical character recognition. When you go to the bank and you insert your check into the system and it can read how much you want to deposit and who you are, that's optical character recognition. And this stuff has been around for 20 years. It was around when I was a postdoc, these convolutional nets. Here I have an example of LeNet 5, which is a pretty famous paper by LeCun, Botu, Bengio, and Hofner, 1998, Proceedings of the IEEE, which is Electrical Engineering Society. And let's just sort of review how this works. In a convolutional net, let's say we're trying to recognize the letter A, which is a 32 by 32 pixel. And in this case, just black and white. We feed the pixels into a convolutional layer, and we get a variety of feature maps, which detect very, very low-level features. We then perform subsampling, which today is mostly done by max pooling. And this gives us a series of a downsampled result. We then apply another convolutional layer on top of this, and then another layer of subsampling. And then we put this into a couple fully connected nets, overall giving us 5 networks, hence the term LeNet. And this is a pretty standard architecture. It's been around now for 20 years, and amazing, it works really, really well. Of course, one can make the layers much, much larger, and there's lots of fancier things going on, like skip connections, but this is the basics. Now, what's really important for this talk is to understand how convolutional nets give us spatial invariance. I'm going to remind you that convolutional nets have 2 very important properties to do this. First, they share weights. When you form a series of convolutions across the image, all those convolutions in each of these layers, each of these convolutions in a layer, these squares here, these 2 by 2 squares, share the same weights. And they also implement max pooling. Let's just review what max pooling is. If I have this single depth slice and it's a bunch of pixels, and these numbers represent the pixel intensities, if I run max pooling on this red box, I select the value of the pixel with the greatest intensity and I return it. So I get a 6. I do this over the entire slice, a max pool of 2 by 2 with a stride of 2, and I get this, I get this 2 by 2 array with the maximum values at each of the pooled areas. This is how convolutional nets share information. Now, according to Hinton, a vision system needs to use all the same knowledge at all locations in the image in order to be successful. So in a convolutional net, it shares information by sharing the weights across the image, and we get this sort of gross spatial invariance by doing this, which I'll explain in a little bit. Now, what's a lot of people may not realize is that convolutional nets are based on a hierarchical model of the visual system. In this case, I took a model I remember from the late 90s called HMAX, Rice, Uber, and Poggio. And in this case, we're going to look at our understanding of how the human mind, really the primate visual system, cats, monkeys, process visual information. So here's a picture of the brain. This is your eye up here. An image comes into the retina where there's some basic edge detection, passes into the thalamus, really the lateral geniculate nucleus, the LGN. From the LGN all the way to the back of your head where you have the visual cortex, which is broken up into various divisions, V1, V2, V3, V3A, and so on. The idea is that our understanding, our experimental understanding of how the brain works is that when an image is processed in V1, little feature maps are formed. And these feature maps can select things like horizontal lines, vertical lines, diagonal lines, and each neuron is activated when seeing certain kinds of little features. And there are some great videos on YouTube which describe a lot of these really early experiments looking at things like the cat brain and the different neurons and how different neurons in the cat brain would respond to certain kinds of very, very primitive features. What's thought is that happens is as information is passed from V1 to V2 to V3 in the visual cortex, there are feature maps formed. So that, for example, when you go from V1, V2 to V2, V4, which are these sort of layered folds in the brain, you get higher and higher level features. And so the neurons are able to describe higher and higher level, gross level features. Now, of course, this is something we recognize from our design of convolutional neural nets. It's exactly when people talk about something like a net, there's this notion that each layer in the neural network is describing a higher and higher level of features. And this is essentially the idea of where this comes from. Now, where does max pooling come from? In fact, max pooling, is much, much older. Max pooling dates all the way back to 1962, which was proposed by Hubel and Weissel. If you haven't read Hubel and Weissel, I really recommend doing this. Hubel and Weissel won the Nobel Prize and for developing our understanding of how basic neurons work and how the brain processes information. It's really classic stuff. Nobel Prize, I think, 1981. If you're going to be doing any kind of neuroscience, you need to have at least a basic understanding of what these guys are doing. In this case, we have a hierarchical model of the visual system just at the level of neurons and neurons connecting to other neurons. Of course, we know that neurons connect this way because you can see them. You look at the connections in a biology lab. So the question is, what's going on? How do they work? Well, you can imagine you have, in this image, these yellow circles represent center surround cells. These are little cells, neurons, that pick up small piece of information in a very small receptive field. Sort of like a flashlight going over. You have a flashlight and you're looking through your room and you see little areas. The flashlight is the receptive field that the neuron in your eye is seeing. The neurons, your eye is seeing this receptive field that gets processed in the neurons in your visual cortex. And the idea is that there are a number of neurons at a very basic level that see simple features. When they pass this information on to a higher level neuron in another layer, the information is pooled. So the proposal is that you have a type of max pooling going on in the neural system. And as information is passed from one layer of neurons to the other, there's a type of pooling which gives a kind of crude translational invariance. And so the idea is that this understanding of how neurons process information was proposed even before I was born, and has propagated into our understanding of why we build deep nets the way we do. So max pooling is a really fundamental idea. And what we're going to do today is we're going to get rid of it. We're going to replace max pooling, at least in this form, with another kind of pooling which is much more mathematically sophisticated. And this is the genius of Hinton. But still, let's sort of look at our current understanding of how this Hmax model would map to something like a convolutional net. Here you have these lower level V1, V2 features, and they would map to your initial convolutional net down where the features are formed, these feature maps that are formed by your convolutional layers. Now, we also have something called a hypercolumn, which we're going to talk to in a little bit, and this is sort of the key to understanding how to implement a more sophisticated system. When we go from one convolutional level to a layer to another, we perform this pooling, and the pooling gives us a whole other set of feature maps. And we believe that there are these sort of feed-forward and feedback connections in the brain so that these layers are really interacting with each other, both through feed-forward and feedback connections and these lateral connections, which give us the ability to process information. So if this is all great, why is max pooling bad? Like, what do we have? What's the problem with max pooling? Well, one of the things we believe is that the brain embeds information in rectangular space. I mean, we live in 3D space. Why wouldn't the brain process information in 3D space? And we can do experiments on humans to figure out what kind of information we can process. And what we find is that when we ask people to translate objects around, that's pretty easy. That's pretty easy thing to do. Asking them to recognize objects that have been rotated, however, is a little more complicated. It takes a little more time. By hard, I mean it takes, I think it's maybe 100 milliseconds or something like that for the brain to process. I might be off on the number. But the idea is we can do basic experiments, on students in the university, and we figure out how the brain processes information. Now, convolutional nets, they can give us a very kind of simple, crude translational invariance. So this simple translational invariance, it might work fine in the lower layers of V1, V2 of the visual cortex, but not the higher layers. The problem is conv nets, as we know them now, have no information about the orientation of an object. Which direction is the object oriented? In fact, a conv net cannot distinguish left from right. So what Hinton, he calls this pose information. And the idea is that the visual system should somehow have a way of representing this pose information, the orientation of objects, and it should somehow share this information across the image. So we're actually going to try to replace max pooling with some other type of system that has this pose information. And I'll just make a side comment that max pooling is a lot of people use max pooling, but in fact, there's some research papers coming out now that when you have like pixel nets and you form large numbers of pixel nets, you don't need the max pooling. It still does pretty well. So max pooling, it seems like it's like a mainstay. It's a foundation of neuroscience, but maybe not. Maybe we can do something else. One of the older hypotheses about what we might do, like how might we go about this, is called the two streams hypothesis, or the dorsal ventral hypothesis. And I've put a little video here on the YouTube video, a link to a University of Chicago video that talks about what this is. I'm just going to kind of review it briefly. The idea is that we have two systems in our mind. We represent where objects are in space, that's the dorsal system, and what the objects are, the ventral. And there are different parts of our brain that do this. So, for example, if we're looking at a boat or a house, is that a boat or is that a house? That's the ventral system. Oh, the boat is out there in the bay. When I look out my window, I see the boats in the bay. That's the dorsal system. Where there are houses and apartment buildings sort of over here, not so far, not as far away as the bay. That's the dorsal system, where they are. How in the world would we know this? Well, a lot of this information about how our brain works actually comes from people with neurological disorders or have had brain injuries. When I was in grad school, there was a book that came out called The Man Who Mistook His Wife for a Hat. And it was about all these curious things that happen to people's minds when they have injuries, like literally like a railroad spike goes through your brain. You're still alive, you're able to function, you do weird things. one of these examples of this, one that Hinton brings up, is simultanegesia, which means that you can only see one object at a time. And that would be kind of weird, looking out and you're looking at my windowsill here and I have all these different kind of plants and I only see one of them. That would be very, very strange. But that's the kind of things that happen when people are injured. It gives us an idea of why our brain has two different object processing pathways, a dorsal and a ventral system. There's lots of evidence of this as well, and Hinton has talked a lot about different kinds of things in his videos to argue for this. But we're just kind of going to go with this. And we're going to look at where might this be implemented in the brain. Well, recall I told you there were these little columns up here. We go back, this hypercolumn. It turns out if you look at pictures of the brain, there are these cortical microcolumns that occur through the cortical layers of the brain. There are about 180 to 120 neurons in each cortical column. In V1, they're actually twice as long, so a little larger. And they all share the same receptive field. That means that if you have the flashlight and you're pointing the flashlight in the dark, that their cortical microcolumn, each column shares that receptive field that the flashlight is highlighting. And again, this is a very, we've known about this for a long time. I've put a review article here from Science that discusses our current knowledge of cortical microcolumns. But this was part of the Nobel Prize for Huber and Weissel. We've known about this forever. But Hinton has an interesting hypothesis. These capsules could encode gross level features like orientation, scale, color, velocity, the kind of features you might see in a traditional object detection system like a SIFT features. He thinks maybe these capsules are encoding them. So we're going to try to build a system that actually has capsules. So instead of doing max pooling, we're going to have capsules. Now, he's been working on this for a long time. I dug up this paper by Hinton, 1981, parallel computation that assigns canonical object-based frames of reference. This is some old stuff. And you can kind of see here, there are these object-based units, and they kind of come down. You get positional size, these little vectors, and the vectors point the direction. So the idea that there are these vectors, the retina comes in here. These are the base level features that connect the neurons that create vectors, and then the vectors form objects. So Hinton describes this as a kind of inverse computer graphics. The idea that your brain would form little orientational vectors as you're looking at things. Very old idea. The notion of inverse computer graphics. Well, what's the idea here? Imagine you have a wireframe of something like a cup. So we have a cup, and the cup is sort of moving around in space. And we'd like to describe how it moves. Well, if you have a rendering engine, the rendering engine has a matrix, like a 3D matrix, a rotation matrix, and maybe a 4D matrix, which can describe scale and skews and things like this. It's a matrix of pose information. And the idea is that when you render an image, you need to have this matrix to know how to render it. Well, Hinton proposes that our brain sort of does an inverse computer graphics, and when it looks at an image, it is able to infer that matrix of pose information. And that matrix of pose information is somehow encoded in these cortical microcolumns. The other thing he talks about, and this is a little more from the mathematics side, the importance of equivariance, the difference between invariances and equivariance. And I'm going to explain what that is. Recall, we talked about the idea that max pooling gives us a type of crude translational invariance. How does that work? Well, let's suppose that we have our original example I showed of max pooling, and we shift all the pixels 1 pixel to the right. And then we apply our max pooling, but over the same regions, the same strides, the same filters. The result we get is quite similar. Instead of a 6, we get a 5. We share the 8 in green. The yellow is a 2 instead of the 3. The blue is 3 instead of 4. The values aren't identical, but they're similar. So you get a kind of crude invariance. So the neural system, if you have an image and you sort of shove it or rotate it or move it a little, it doesn't change the outputs that much. It changes a little bit, but not that much. That's what we mean by max pooling gives us a type of crude translational invariance. What is an equivariance? An equivariance is a mathematical generalization of an invariance. It's an invariance under a similarity transform. A symmetry transformation, like a similarity transform, an affine transformation, etc. If you're like me and you had to study years of advanced mathematics, I actually have a degree in math, you would recognize this as a group homomorphism. F of g of x is g of f of x is f of g of inverse. If you study geometry and you're looking at a triangle, the centers of a triangle are invariant under similarity transforms, and the centroid is invariant under an affine transformation. The statistical argument for this is actually a little more interesting. The mean of a system is invariant in the number and the change of units. How much money do you have? You have dollars, you have Bitcoin. As long as you compute the mean fast enough, the mean doesn't change. The median actually is generally a better statistic because it's more invariant under different kinds of transformations. It's invariant under all monotonic transformations. So max pooling provides spatial invariance, crude spatial invariance, but Hinton argues we need spatial equivariance. How are we going to do that? Well, in his first paper, we're going to define a vector called a capsule vector, and we're going to use it to define an affine transformation. How is this going to be useful? Well, one of the things you're able to do in his work is you show that you can segment highly overlapping objects. So you imagine if you have a training data set like MINST, but instead of training it on numbers, you train on overlapping numbers. So for example, you train on an image which has an 8 and a 7, a 9 and a 4, a 9 and a 5, an 8 and a 4, and so on. And it turns out that this is really, really hard to do with a convolutional net. But with this new capsule network, it actually works really well. And I'll show you some results of this. It's actually able, like we're able to distinguish these numbers quite well. So what Hinton says, by the way, he uses this term called explaining away. When he talks about it, he says, because where if two hidden causes are independent, they can become dependent. When we observe an effect, they can both influence. So here he's talking about, he talks a lot about this explaining away. It's an old idea from Judeo-Pearl logic. But here what he means is that you're just able to disambiguate the two images. So. All right, let's take a look at the architecture of a capsule network. We're going to take something like our original ReLU Linnet type architecture where we have images coming in. We have convolutional maps. The convolutional maps would normally be max pooled, but instead of max pooling them, we're going to convert the maps into vectors. So we call these primary capsules. So instead of applying the max pooling, we're going to replace that with just transforming the convolutional maps. We're just going to reshape them into vectors. And then they get mapped into something called digit caps, which is a higher order capsule network. And then there's a max norm loss, an L2 norm loss, which allows us to do classification. So again, we're going to train this on something like a MINST data set. They're going to be 10 classes, and this is what the architecture looks like. However, we're also going to have an unsupervised part where we try to actually reconstruct the images. And the unsupervised part of the network is going to have take this digit caps, pass it through a couple of fully connected units with ReLUs and into a sigmoid, which gets us back to the original image. This is the general architecture of the system. And it's a combination of supervised and unsupervised losses. So it's sort of a hybrid. I'm going to go through this in detail with you now. So the first idea is that we have these capsule networks. We start with something like a typical convolution. We have conv2D, and then we do max pooling. We're going to keep the first convolutional layer, but we're going to replace the max pooling with a vector. So we're going to take these convolutional TD maps and we're going to reshape them. We're literally just going to say like keras reshape, and we're going to get primary capsule vectors. Then we're going to have another set of vectors, which is the second layer, which is the digit caps. And we're going to connect them by a special routing algorithm. And the routing algorithm is called routing by agreement. And this is the key to getting this to work. And it's a very, very interesting algorithm. It's a very interesting variation on backprop. We're going to go through it in quite some detail. So the first part to realize is that we replace max pooling with vectors. We just reshape our convolutional network. And sort of the way that Hinton says is that active capsules at one level, which are red, make the predictions, and then via transformation matrices for the instantiation parameters of the higher capsules. So in other words, the red makes predictions because it assigns the pose to the features that it sees. When multiple predictions agree, when the predictions of the red agree, these different predictions agree on what it sees in the blue, there's a feedback loop which makes the blue become active. So this is not a fully connected area. The layer primary to capsule is not fully connected, but the connections are pruned by the routing algorithm. So let's take a look inside keras and what's actually going on here. Here we go. We have keras. This is our primary cap. This is, by the way, I've taken this keras implementation from Geoffrey Gao. Forgive me if I pronounce the name wrong, but it's called CapsNet keras. And just an implementation of this, which I'm going to go through with you. So to define the primary capsule, we have our output layers, which are convolutional filters, and they're dimension number of capsules by number of channels. So whatever the number of capsules we have are and the number of channels are, in this case 8 by 16, that's how we define our convolutional layer. And then we reshape the layer by the dimension of the capsule. And then we squash it, and we do a squashing function, which I'll describe in a bit. But the idea is that all we did was take this convolutional layer and reshape it. So we took the output of a conv2D layer, reshaped it to get vectors. Pretty clever. Now, the idea of a capsule is these vectors that we've reshaped can represent poses. They represent the directional orientation of an object. In particular, there's a data set called the small norb data set. They represent images of the same object taken from different perspectives. So, like a lion, here's a guy shooting a gun, an airplane, and a car, and different perspectives. And the idea is that the capsule would represent a vector of orientation representing the orientation of these objects. And in fact, later, in the later paper, the second paper, they replaced the vectors with entire matrices. They call it matrix capsules. And this actually gives the best accuracy on the small norb data set. It improves the error by 45%. So it's a pretty big advance in this particular area of image recognition. Now these vectors don't just capture orientation. They capture the values of the vectors, capture different kinds of information. And we know this because we can take an image that we feed in, and we can perturb it a little bit, and we can see in certain ways, like we can change its scale and thickness. We can localize part of it. We can change the thickness of the stroke. We can skew it. And by doing this, we see different capsules activate. So the idea that a capsule is a group of neurons whose outputs represent different properties of the same entity. And in fact, these properties, if you used to do image recognition with SVMs, these are SIFT-like features. So the idea is that we're explicitly learning SIFT-like features for the objects that we have in our data set. Now, Hinton talks about something else which is a little confusing. I want to go through it in some detail. He talks about the difference between place coding and rate coding. And what he means by that is that if you look at a convolutional net and something without pooling, and you look at the low-level features, they represent features for small receptive fields. So imagine you have the flashlight again, and you're pointing the flashlight. When you point it from one area to another, different things will light up in the room. There's your couch, there's your chair, there's your TV. Each of those gets assigned to a separate receptive field. In this case, for example, the field, I have like a vector for a triangle and a vector for a rectangle. And these are primary capsules. This is called place coding. Each position maps to a specific active capsule. However, once you get to the next layer, you don't want to do place coding. You want to do rate coding. Now, rate coding is an idea, again, that goes back way back to 1926, traditional neurological way of coding. What does it mean? It means that if you have a neuron and you give it a stimulus of some kind, in other words, you have a cat brain, you open the cat up, you open up its brain, you attach an electrode to it, and you show it an image, certain neurons light up. The stimulus that lights up is actually encoded in the rate of firing. This is a very, very fundamental thing of how neurons capture information. They don't capture by intensity, they capture by the rate. Now, there are actually other kinds of coding schemes, but this is the most traditional. So what Hinton means is that somehow, when you get into the higher layers of your network, things that were original, the lower level can represent places, but as you start getting into objects, this should be rate coded. And for him, the rates are encoded in the vector values. These capsules encode the output, they encode the rates. So for example, if I take a rectangle and a triangle, I put it together and I get something that looks kind of like a boat, like a sailboat, that boat is now rate coded. So this is what he means. And it's kind of an interesting aside to this. One of the things about neural networks, why they work so well, is that we use ReLUs, rectified linear use, instead of sigmoids. Why do we use sigmoids? Sigmoids were actually suggested by Jack Cowan, who's a friend of my graduate advisor at Chicago. And he suggested them for neuroscience. He was actually doing things like statistical mechanics of neurons. He had no idea people would ever use them for making neural networks in backprop. They were just something he used to model neurons. Later, people started suggesting using rectified linear units, and maybe and this also comes from neuroscience, and it took some time for the deep learning guys to pick this up, the neural network guys. Maybe the ReLUs are implementing a kind of rate coding also. Maybe that's why they work so well. No one really knows why ReLUs work so well. Is it just an engineering trick, or is there something fundamental going on? Nevertheless, Hinton goes to a great deal. This is part of his motivation, is understanding that, look, there are ways in which our neurons encode information, and we're trying to build a mathematical model that represents what we see in the brain. And this is the idea. Now, in order for this to work, we have to have this routing algorithm, which is we have a hierarchy of parts which is coupled. And I'm going to kind of explain this using some ideas from a really nice video I saw, which uses this triangles and rectangles to go through the description of the routing algorithm. And I'll put a link to that in here so you guys can watch it too, because I don't want to make this video 5 hours long. But the basic idea is that we have a rectangle and a triangle, and each of them gets a capsule vector. Now, what is actually being seen? Is it a boat or is it a house? Well, if it's a boat, then the vectors are oriented, the triangle's oriented one way. And if it's a house, it's oriented another way. And so these U vectors get passed up to they get passed up to the V layer, the parent capsule, the digit capsules in our case, the parent capsule. But there's a transformation matrix associated with them. And that gives you the pose. And the primary capsule, when it connects to the parent capsule, will guess this pose information. And the parent capsule also assigns a vector, but it assigns a vector to the whole object. And that vector has an orientation as well. And the idea is that the vector that's in the parent has to somehow match the vector that's in the primary capsule. And so as the primary capsule is guessing these different poses, the parent says, yes, okay, I agree with you. It gives a feedback, and it prunes out the bad poses. So in other words, a higher level entity is present if the lower primary layer capsules agree on the predictions for their pose. And so what we're going to get here is we have, when you go into the paper and try to read it, you're going to see this mathematics like the output is a mean value of u hat of j given I is the prediction of the pose of j given the vectors I and this pose matrix, this transformation matrix. And Vj is a type of nonlinearity applied to that prediction, a weighted times a weighted sum of the predictions, and we're going to learn these weights, and then a nonlinear area applied to it. So the routing algorithm, I kind of spelled that wrong, but routing algorithm, some prose, meaning I want to talk some of the things that Hinton says. He says, well, it's just kind of ways to understand this. A capsule is activated only if the transformed poses coming from the layer below match each other. There is a more effective way to capture covariance and leads to models with fewer parameters that generalize better. Once again, a capsule is activated only if the transformed poses coming from the layer below match each other. This is a more effective way to capture covariance and leads to models with fewer parameters that generalize better. Another thing. This is an effective way to implement the explaining away that is needed for segmenting highly overlapping objects. An effective way to implement the explaining away that is needed for segmenting highly overlapping objects. Now this next one comes from the later paper, the matrix paper. The routing algorithm is like an attention mechanism. There's a competition, and it's between the higher level capsules that a lower level capsule might send its vote to. So there's a feedback loop between the higher capsules and the lower level capsules. So there's a competition. It's not between the lower sending votes to the higher. It's between the higher level capsules that a lower level capsule would send its vote to. So which higher level capsule gets the vote? This is a powerful segmentation principle that allows knowledge of familiar shapes to drive segmentation rather than just using low-level cues such as proximity or agreement in color and velocity. Once again, the routing algorithm is a powerful segmentation principle that allows knowledge of familiar shapes to drive segmentation rather than just using low-level cues such as proximity or agreement in color and velocity. So there's some of the stuff that Hinton says, which I thought would help to try to understand the routing algorithm. Now, let's go through the math. We start with the network, and here we have the input X coming in. This is our data. This first layer are the primary capsules. These are the second layer are the parent capsules. What happens? Data comes in, primary capsules are activated. We get a U. We then compute the weight. We then compute the weight of the routes. So we have to compute for all the U's. We compute their mean weighted prediction. We have a W matrix. We've guessed that we're going to learn this W matrix through, of course, gradient descent. So we start with a W, and we get a mean value for this J. Given all the U's, we get the mean value, and we compute Bij, which iteratively is just an update equation between Uij and the output of this. So in other words, we're going to try to compute the connections between the primary layer and the parent layer. The Bij's, we start. So this is an iterative thing. So we start off with Bij as just some guess, and we compute the Cij's. And the Cij's are just a soft max of the Bij's from our initial guess. Sij, then we also have an initial guess for W. So we get a Uij. The Sij's is just a weighted sum. So our initial B guess goes into the Cij's, and our initial W goes into this U bar, and we get an S. We then apply a squashing function, and we get a V, which is our output. We then do this again, and we update the B's. And so we then do this again. We update the B. We have the same X. It's the same X. But we update the B, and this time, as we update it, we're actually able to remove some of these B's become very small, and they disappear. And if we do this 2 or 3 times, only the blue lines, for example, in this example, remain. So the idea is that for each given X data that comes in, we come up with a specific set of B's. which are iteratively formed by multiplying the mean value of uj given I times the output of j. And we iteratively update this until we prune all the connections for that specific data point. So the CIJs, which are these weights, that connections, are determined by an iterative dynamic routing process. So let me do a little comparison to give you an idea here. In a traditional network, we have an x and we get a scalar, and that's the input. In a capsule, we have a vector. We then can apply some transformations. We can apply an affine transformation. U bar, U hat, j given I equals wij times ui. We don't have that in traditional neurons. There are no affine transformations. Remember, the only way that we get translational invariance or invariances are by these little rotations. There's no equivariance. We then can apply a weighting. We say that Sji is a weighted sum of these average u's. Well, this is just like wx plus b. This is just like the w's come in and you sum them up. So here the u's are coming in, we get the u bars, they get summed up by the c's. So this is just like what happens in traditional pre-activation layer of any network. Then we apply a nonlinearity. In a traditional neuron, this is usually a sigmoid, maybe it's a tan H or a ReLU. So, there we go, sigmoid, and this is the nonlinearity. In a capsule, we apply a squashing function. And the squashing function is a type of vector nonlinearity. It applies to vectors, not to scalars. The output of our capsule is now a vector, whereas the output of a traditional neuron is a scalar. So the capsule networks, at least in the first paper, are a vector generalization of traditional neurons. They're just like regular neurons, but they output vectors, not scalars. Anyway, I took this from this nice GitHub repo, GitHub Naturomics CapNets, which is a TensorFlow implementation of CapsNet. I decided to go with the keras one for this to keep this presentation down to at least an hour. So what is this affine transformation? How does this work? Well, let's imagine we have these primary capsules. And on this dimension, we have a triangle, and here we have a rectangle. And we can imagine if we orient the capsule in one direction, we get a house. If we orient the average of these two, so this is a U, this is a UI, and this is a UI. And if we form this mean, one orientation would give us a house, and another orientation would give us a boat. And so for each pair of UI primary capsules, we get this transformation matrix. And this matrix can do things like it can represent rotations and skews and deformations. And the idea is that the primary, in this case that we use rectangles and triangles, these capsules or prediction vectors are routed to the parent layer, which are object vectors, boat and house capsules. And then the routes are pruned. So in other words, if we're looking at a boat and not a house, we get rid of this connection because we want to remove it. And so CapsNet is moderately robust to small affine transformations in the training data. By pruning these routes, we guess the affine transformation, we prune the routes, we actually can have some equivariance. There's also this idea of a squashing function. What is the squashing function? Well, it's Sj norm squared divided by 1 plus Sj norm squared times Sj over norm of Sj. So it's like a normalization. It normalizes the output vector V, which again is this mean value, the sum, this weighted sum of the mean u's, but it squashes it. So the squashing vector is a vector nonlinearity. And the idea is that, the length of the capsule is proportional to the probability that an entity is being represented by a capsule. So the length of the capsule is actually important. But we're gonna apply this squashing function to it. And there's a nice little blog here which talks about understanding Hinton's capsule networks and a nice discussion of the squashing function if you want to do a deeper dive into this interesting vector nonlinearity. But the point is that this is the nonlinear, just like you have ReLUs and you have sigmoids. The squashing function is our nonlinearity for our vector capsule network. Now we have to talk about the magic of this algorithm, which is routing by agreement. And the idea is that we're going to select data-specific routes by matching the primary outputs and the secondary outputs, which are these squashed outputs. So, here we might, from the left, you have examples of primary outputs, guesses, various vectors representing the triangles and rectangles in our image that we're looking at. And when we average them, we get these U vectors here, these U bar vectors. And this is our expected output. However, the expected output might be, for example, this boat. But there are these other poses of the image which simply don't match the pose that we're guessing. Remember, we're trying to learn this affine transformation. And if we look in the second layer, well, these different poses that don't match. And so the idea is that somehow we have to relate the output of the first layer to the output of the second layer. And in the first paper, this is done by just cosine overlap. So the overlap, and what you do is when the overlap is, when this is too far away, the overlap is too small, you prune it away. So you get rid of this. And as you prune iteratively, many of the routes disappear and the upper layer starts to guess the correct pose of the object. And so there's this feedback loop. Now, the second paper actually does something a little more sophisticated. When it matches the primary outputs to the secondary, it doesn't use an overlap. It actually uses a free energy cost function. And there's actually a really subtle reason for doing this I'm going to explain, which is related to some other research, which it doesn't talk about, but I'm going to tell you about it anyway. So here's an example of the routing algorithm from the paper. The idea is that we have this fixed point equation. The BIJs are connections between the primary layer and the secondary layer. And remember, eventually we're just going to take a softmax on them. So, but there's an update equation. Every time we run this, every time we run the algorithm, we go through it 1, 2, 3 times. We get a new U bar, new V's, new U hat, and new V's, and so we get new BJs. So let's look at the routing algorithm. So procedure routing for a given U hat J given I, and then the, let's just go through it. For each capsule I in layer L, so each I, and for each J in layer L plus 1, this is J, we initialize all of these connections to 0. So there are no connections at all. Then for each iteration, we're going to go R iterations, usually 3. R is 3. For each capsule in I, we're going to compute, in the layer L, we're going to compute the CI softmax. We're going to compute the softmax. Not a big deal. For each capsule J in the next layer, we're going to compute the output S, which is this weighted sum where we of the U hats, where the U hats were computed given our initial guess of W. And I didn't talk about what that is, but that's okay. Then for each capsule J in the parent layer, we're going to squash the output. We're going to get the squash. No, we're going to apply nonlinearity. Then for each capsule I in the layer, in each capsule J, so for all n-squared connections, we're going to update the BIJs by saying you only get a value. They only get value if there's a strong dot product between the U hat and V. And we're going to do this 3-4 times, and that's going to give us these nice blue connections, and the rest of them will just stay 0. Now, how would we implement this in backprop? That's kind of the trick, right? I mean, we're going to be doing SGD training. We need to implement this in backprop. So what's going on? Well, we can imagine that the routing algorithm is like a fixed point equation for expectation maximization. So we have a fixed point equation, and we're going to, and in fact, it kind of looks like an energy. It kind of looks like UWV. If we look at the B here, and I just sort of put in, I just sort of replaced the W into the U, it kind of looks like B plus some energy term. So it kind of looks like a log likelihood. And what happens is we're going to expand this 3 times. We're going to run it 3 times. So instead of running EM to some stopping point, we're just going to run it 3 times. And in fact, This is very similar to a blog post I wrote which talks about the fixed point equation for the tap free energy in an extended mean field restricted Boltzmann machine. And I'll make a video on this at some point. But the point is that you get something that kind of looks like an energy, and then you run expectation maximization, you get a fixed point equation, and you unravel it. In fact, in the later matrix capsule paper, they actually use a free energy. And they actually Hinton writes down a free energy explicitly to do this. When you unwind the fixed point equation, you could think of it conceptually as having 3 layers that you've unwound. You've unwound the network to have these, as if it's having 3 layers that are unwound, and they all share weights. They all share the weights W, which form the U hats. And you're just unraveling this. And so it's kind of like a 3-layer fully connected network, except, the network's not fully connected, with shared weights. And then you can just run backprop on it. And that's exactly what they do. Let's take a look in detail in keras at what exactly is going on. So in the keras implementation, first thing we have to do is we have to implement a layer. So by doing that, we have my layer as an example. I took this example from writing your own keras layers. We have the layer, and we have, you have to make it a init function. You have to have a build. So the build has to have, the weight, they call it a kernel, and the initializer. So it's just uniform initialization. So now we know how we initialize W. And the shape. And then there's a call function. The call function is what actually is called in backprop. But when backprop it does the forward pass, it implements the call function. The call function returns a keras tensor or a TensorFlow tensor, keras tensor, and then backprop is run on, you build the computation graph, and backprop is run on this output. So the output of this in this one, for example, is just k.x. That's the simplest the simplest type of thing you could do in an example. And then you have to get the shapes. So here's a reduced form of the keras of the routing algorithm in keras. Let's take a look in detail. We start off with our call function. We get our inputs, which are just this array, and then we tile them. I'm going to kind of skip that. And then we get the hat. So the inputs hat is just a function, which is batch dot. It's a dot product between x and w. That's it. But it uses the elements that have been tiled. And that's because we started off with this convolutional net. So we kind of have this little detail here I won't go into. But the point is that this is how you form U hat. And then you're going to have a stop. You have to say stop the gradient. You're not going to run a gradient on this because we're going to act on gradient U hat. Instead, we're going to run 3 iterations. So we say we get B is just 0. Recall I said the BIJs are zeros. And they're initialized by an array of num capsule times the, let's just say that they're initialized. And we start with num routing, which I said is 3. That was the R. We then compute the softmax of B, and that was the softmax. We then go through the iterations. We compute the squashing function. The outputs are the squash of dot C times the input hat. So that's this, C times U hat. And then you have to reshape. And there's also a case on this, and then there's the last case where you have to say input hat stopped. So, I'm sorry. You do this one first. First you do the B update, and then when you stop, you do the squashing. I'm sorry, I did it in reverse. So you start here, you do, if you're not at the last step, you compute C dot hat, and then you update B, which is just B plus U hat stopped times the output V. And then up here, if all you want to do is get the S's, you just squash them, and you don't actually have to update B on the last step. And so that's the implementation. I may have a little confusion. I was not expecting the squashing function to be applied to the hat. So I may have to go back and double check that. So let's just, but that's Yes, that's correct. Just wanted to double check. When I was in college, I had a math professor once go to check an equation, and he said, "This is trivial." Walked out of the room, came back 30 minutes later, and said, "Yes, this is trivial," and continued. So yes. So the point is that the V's are the things that are squashed, and this is what you need. And so on the first iteration. In the second iteration, you implement the squashing function, you get the V, and then you compute the update to B. On the last iteration, you just compute the outputs. In the later paper on matrix capsules, instead of having a dot product which represents these distances, you have a cosine distance. The cosine distance is replaced by a free energy. What's that? Well, that energy is just a cluster score. It's the score of the probability that xi given a mixture model minus xi given a uniform distribution. That is, you represent all the data points using a very large Gaussian mixture model. And the cluster score is just the probability of x of I being represented by that mixture model minus it being represented by a uniform distribution. And that's actually a type of free energy. And you can go and read the paper and listen to some of his videos and go into some detail about that. But the idea of the mixture model is basically the probability is just a Gaussian distribution. So PIH is the probability density of the H component of the vote from I under the capsule's Gaussian model for dimension H, which has variance sigma H squared. So in other words, you generate a whole bunch of Gaussians. You put the Gaussians on all the data points. The idea is that expectation maximization can then find the mean and the variance and the proper mixing proportion of the Gaussians, and that this is a better score. That when you use a cosine function, you can get results that are good, but they're not great. Cosine isn't really discriminative, and when you use a free energy, you get a much better discriminative score and you get much better results. And the idea is that data points that form a tight cluster from the perspective of one capsule may be widely scattered from the perspective of another. And so we want the cluster score to be able to tell us when the primary outputs and the secondary outputs cluster in the same way, and to remove these outliers. And when you do that, you get a much better result. And that's the intent. And again, you go through the same idea that you write down the free energy, and you can do expectation maximization, and you can do a three-term relation. And it's all very, very similar to the vector case. And in fact, it works really, really well. This is a result, but the result is actually from the matrix capsules paper. And to give an example of looking at a human, an animal, a human, a plane, a truck, a car from the NORB data set, and you can see just after 3 iterations, the capsules start to converge to the correct classes. So you don't need to run expectations more than 3, and that's their argument. So it actually does very, very good. So the best result, in fact, I think there is on the NORB data set, if I'm correct about that. Now I want to take a look, go back to the architecture. We've talked about this routing algorithm, this dynamic routing algorithm. Let's go back to the capsule architecture, the network, and take a longer look at some of the loss functions. Because you design the network, but you got to have a loss function. So there are 2 loss functions. So here, we have our input, our convolutional layer. We reshape the convolutional layer to give us vectors, and the reshaping is the same dimension as the convolutional layers. We then get these digit caps, which are our primary capsules, and then we know that the length of the vector capsule is proportional to the probability that we see a digit. So do we see a 1, a 2, a 3? The length of that vector is proportional to it. And we're going to have an L2 loss function here. It's a, forgive me, I'm stumbling. It's a max margin type loss. It's a margin type loss function. You can look at the paper. It's a margin type loss function for this, which is a supervised loss. We then have an unsupervised loss as well, which is a type of regularizer. And the unsupervised loss is saying, given this vector, that is this single vector, we mask the digit caps and we pick the largest vector. It's like a max pooling, but it's a max vector. We pick the maximum vector. In other words, we pick the vector with the maximum probability of being something. And then we reconstruct the image from that. And so it's like you were doing an autoencoder and you're reconstructing an image from the latent vector Z in the audio encoder. And we're going to combine this supervised margin loss with the reconstruction loss to build our network. So again, the idea is that we go from max pool. Give me a second here. The idea is that we go from max pool to max vector. So again, imagine this is our collection of vectors in our capsules, our digit caps. I just sort of took this image from someone else and just wanted you to show there's a vector here, which are maximum. This is our maximum vector. We mask it. We run it through our autoencoder type architecture, and we come back to the original size and reconstruct the image. Now, the idea is that that we replaced max pooling with max vector. So we didn't really get rid of it. We just changed it. Let's take a look at the code. Again, pretty simple. The same thing. We have a layer called a mask, and the mask just takes our inputs, which is the x, sum of the squared inputs, the square root of the sum of the squares, forms a one-hot encoding, and then flattens it on the inputs and multiplies the inputs times this mask. So the mask is multiplied by these inputs, and it just highlights this one particular vector. And so you return the mask value. Once again, the idea is that the idea is that these are the labels that you're guessing are the inputs. You do a one-hot encoding on them to get your mask, to get a mask vector. You flatten it, and then you multiply that by the inputs. Excuse me, expand the mask to take the flattened mask, expand it back to a vector, multiply it in order to obtain, in other words, 1 through 10. We get the vector, in this case, 1, 2, 3, 4, like vector 5, and that's the one we're going to reconstruct. How does that appear in the loss function? Well, recall that in keras, when we wanted to find a loss, here's the training of the model. The loss is a supervised plus unsupervised or reconstruction error. So out caps is our margin loss, and in the model, when we say model compile, we specify the loss. So the input, and when we define the model, we specify the inputs to the loss. So out caps is the inputs to the margin loss, and decoder, which is masked by the labels, is the input to the MSE, which is the reconstruction loss. So again, this is our layers. Then again, this is the reconstruction of the mask has occurred. So we pick the most probable vector. We build our decoder, which is a dense layer 512, dense layer 1024. In this case, it's not dense layer 1024. Then dense layer prod input shape, which is 784. Then we reshape them, and then we're going to get our out caps. Sorry, I don't have the out cap shown here, but it's I didn't add that, but I trust me that the next step is to just get the out caps from this. So how well does the reconstruction do? Well, it works pretty well. If you have a minced system that's trained on overlapping images, I can't remember the name of the data set, but they have this data set where they mix all the images up. So this data is an 8 and a 1. This one is a 6 and a 7. And you try to reconstruct the images. If you remove, for example, one of the capsules, like the one that capsule that represents the second digit, only the first digit's reconstructed. So that's pretty good. It does have trouble reconstructing close images, but humans have the same problem. And so that's not bad. And there's a nice little video I linked to which shows the reconstruction, which kind of goes through a little more detail. It's a little 5-minute video which goes into detail how good this thing is at reconstructing overlapping images. Now, finally, I want to talk about this matrix capsule paper because this thing is a lot more sophisticated. I'm not going to go through it in detail today, but maybe in another video or a blog post, I'll go through it. The idea is that the first paper, the vector capsule paper, is not bad, but it's not great. It's not great. So instead, what we do is we replace the capsule vectors with matrices. And the matrices actually have some convolutions in them. And this allows us to build a collection of ReLU to primary caps to convolutional caps. So it's sort of a hybrid of matrix, of capsule vectors become matrices. We add some convolutions in, and we're actually able to get a hierarchy of capsules. And then at the end, we get a class capsule. And I didn't realize I did this, but I listed and then we have the cosine distance gets replaced with this cost function, which is a free energy cost, which I described a little bit earlier. And so there are things like there are convolutions between layers and lots more details. But the point is that there's a lot of advances going on. This is really like just a couple of weeks ago. This is very state of the art. And there's a lot of excitement that matrix capsules are going to be the next big thing in image recognition. Well, look, I really want to thank you for staying through all 44 slides here. I really appreciate it. Please post questions and comments on the YouTube channel. And I want to wish you all happy holidays and a Merry Christmas. And I hope you've enjoyed this talk on capsule networks.